Okay, so calorimetry is a technique. It's something that we do. Calorimetry is used to find energy transfer, and then you use that energy transfer usually to determine the specific heat of a material. So when we talk about this, specific heat is C, and it's the energy required, joules required, to change 1 gram of substance 1 degree Celsius. Joules per gram degree Celsius. So if I have 1 gram of gold and I want it to go up 1 degree Celsius, that requires a certain amount of energy. That's the specific heat. Same thing if I have 1 gram of water and I want it to go up 1 degree Celsius, that requires a certain amount of energy, and that's its specific heat. Every material has its own specific heat. Water being the highest. Water has a very high specific heat because of hydrogen bonding and surface tension and properties like that. Metals like gold, gold is one of the lowest specific heats. That's because of that big electron cloud. It's very easy to change the temperature of metals. Even like things like ice and water vapor have different specific heats than liquid water itself. Liquid water is the highest. That's it. You don't need to know much more about specific heat besides it's an intensive property. It is always the same for a material, and it's the energy required to change 1 gram 1 degree Celsius. We can use it to find what material we have. You've probably done an experiment like that in physics if you've had physics. We talked about it in chemistry 1A, but you basically just change the temperature, see how much energy it took, and that's your specific heat. We use this equation, the heat equation, Q equals mc delta T, when we're doing calorimetry. Q is the amount of heat required, or energy, in joules. M is the mass of the substance in grams. C is the specific heat. And then delta T is the temperature change. Final temperature minus initial temperature. And this could be in Kelvin or Celsius. Why can it be in either Kelvin or Celsius? Hi.
I'm just going to give this to Scotty.
That's fine.
I forgot to do your assignment for tomorrow. I totally spaced that. Thank you. Sorry.
You're good. Why can it be in Kelvin or Celsius, Emma?
Because Kelvin and Celsius, like 1 Kelvin is the same as 1 degree Celsius.
Right. So Kelvin and Celsius, whenever they change together, but Kelvin is just 273 higher. They go up together. So a change is going to be the same amount. It doesn't matter. Questions about this formula, equation, whatever? So these are directly related. Bigger masses require more heat. Does that make sense? Yes. If your specific heat is higher, more heat is required. More energy is required. If you want a bigger temperature change, that's going to require more energy. So these are all direct relationships. Good? Okay. Okay, so yesterday, if you watched the video, you saw that I talked about closed systems. And starting this semester in chemistry, we have to start focusing more on the system and the surroundings and how those work together, how sometimes we have to ignore the surroundings and sometimes we pay attention to the surroundings. So, Q for the system, we're going to have to very carefully define the system. And a lot of times it's going to be the reaction itself. And we can't look at the water around it. We can't look at the air around it. We're just looking at the reaction. The surroundings will be everything else. The water, the air, whatever. So if the system is positive, that means that the system gained energy. That's endothermic for the system. And the surroundings are negative. That means that the surroundings were exothermic. They lost energy. So if the system gains it, it came from the surroundings that lost it. Does that make sense? And we would call this endothermic. The system gained energy. The surroundings lost energy. And when we're defining endo and exothermic, we're talking about the system. And this gets more and more confusing as we go, so you've got to try to start keeping this straight in your brain. Okay? The opposite is true if it's exothermic. The system loses energy, and the surroundings gain that same amount of lost energy. And this brings, sorry, go ahead.
Did you say the surroundings gain that energy?
Yeah. So if we're talking about an exothermic reaction, a reaction that gives off heat, it gives it off, it loses it, and the surroundings gain that energy. And that becomes very tricky because if we look at something like a reaction in a beaker, the reaction's happening inside the water because it's a solution. When we're measuring the temperature, if we put a thermometer down in here, we're actually measuring the temperature of the surroundings. So you see the temperature go up because you're measuring the temperature of the surroundings. But the reaction itself lost energy and was exothermic. It gave energy to the surroundings.
So you said we're measuring the surroundings with the thermometer.
Right, the water around the reaction. And that's where this all starts to kind of get confusing. Inversely, if we have a reaction that's endothermic, we are measuring the temperature of the surroundings. The temperature goes down because the reaction itself gained energy. It took energy from the surroundings. Christian?
So it's just opposite of what the thermometer reads.
Kind of, yeah. So if the thermometer goes up, that means that the reaction was exothermic. It gave energy to the surroundings. If the thermometer, if the temperature goes down, that means that the reaction absorbed energy and took it from the surroundings. We can't measure the actual temperature of the system because that's the individual tiny little molecules, atoms, particles that are reacting. We have to measure the temperature of the surroundings in this case. And we'll talk more about this. We're going to be very careful in defining our system and our surroundings and what we're measuring the temperature of. Okay? All right, let's do some examples. Propane is the gas that is commonly used in gas grills. A sample of propane with a mass of 44 grams is completely burned in oxygen, and in the process it releases 2,002 kilojoules of energy. This chemical reaction is brought into contact with a water bath, and the transfer of energy from the reaction to the water takes place. Assuming the specific heat capacity of water is 4.2 joules per gram Kelvin, and that in such an experiment 100% of the energy generated by the propane is transferred to the water. So we're assuming it's a perfect system where all the energy is transferred. That's not always true. It's honestly never true, but we're making that assumption. Causing the water temperature to increase, answer the questions that follow. In which direction does the energy flow? Scott?
When it flows from the propane to the water.
Yep. The propane releases the energy. As it burns, the water absorbs that energy. Calculate the change in temperature of 20 kilograms of water. Okay, so we have 2,002 kilojoules of energy being released by the propane and absorbed by the water. So it's a positive for the water, right? Water's absorbing it. It has to be in joules though. So multiply by 1,000. You have like 2 million. Joules equals 20 kilograms of water, so 20,000 grams. C for water, they told us, is 4.2 joules per gram Kelvin. And we want to know the change in temperature, delta T. Kelvin or degrees Celsius. Kelvin in this case because we were given joules per gram Kelvin, but they're the same. So the water temperature goes up 23.8 Kelvin. If it started at 10, now it's 33.8 Kelvin. If it started at 100, now it's 123.8 Kelvin. Okay? Is the combustion of propane an exothermic or endothermic process? Explain your answer. Emma? The burning of propane.
Yeah, because the propane lost energy and gave it to the water.
It lost energy. It gave it off. What's that? It's exothermic. The propane lost energy to its surroundings. So it's exothermic. The water gained energy. The propane gave off energy. So that's exothermic. And that's where we have to be very careful in defining our system and our surroundings. Propane is the system. It gave energy to the surroundings, the water. Questions?